Okay, now let's talk about complex conjugation and its relationship to matrices. This turns out to be quite an important topic in certain areas of physics and in electrical engineering. So let's take a look at this. If we have a m by n matrix, then the conjugate of that matrix is simply the matrix whose entries have all the complex conjugates. So you're taking, how do you read this? You say that the ijth entry of the complex conjugate matrix is equal to the complex conjugate of the ijth entry. When you read expressions like this, you read from outside in. Ijth entry of conjugate matrix is equal to conjugate of the ijth entry. So you can see that example here. Here we have two matrices. Every entry here is the complex conjugate of the corresponding entry here. All right, so take a look and digest that example. Now, it turns out that complex conjugation works the same way with matrices that it does with ordinary numbers. If I add two numbers, take the conjugate, that's the same thing as the sum of the conjugates. Okay, so let's express this in terms of the entries of A plus B. So that's what this is saying. This is the ijth entry of the conjugate matrix of A plus B. All right. Now you define the ijth entry of the conjugate matrix as the conjugate of the ijth entry. Okay. Now we're just dealing with the ijth entry of A plus B. By definition of matrix addition, that's the ijth entry of A plus the ijth entry of B. The conjugation remains the same. Now we're just dealing with complex numbers, so the conjugate of the sum of two complex numbers is the sum of the conjugates. Now we work our way backwards. The complex conjugate of the ijth entry of A is the same as the ijth entry of the conjugate of A. Same with the B. The complex conjugate of the ijth entry of B is the ijth entry of the complex conjugate of B. Right? Then you use finally the property of matrix addition again, definition of matrix addition, that allows you to combine these two matrices and take the ijth entry. Okay. All right. So this proof follows a similar pattern that we've seen with vectors. Now, this one says that if you multiply a matrix by a complex number and take its conjugate, that's the same thing as multiplying the conjugate matrix by the conjugate number. Okay. So you can see that that does work through very similarly. We want to take the ijth entry of this matrix on the left and show it's equal to the ijth entry of this matrix on the right. So here's the ijth entry of alpha A conjugate. That's the ijth entry of the matrix on the left. Okay. By definition, that's the complex conjugate of the ijth entry of alpha A. Now we're just looking at alpha A, the ijth entry, so we can break this out. We know scalar multiplication of matrices. We can take the alpha out. Okay. Now we simply have the complex conjugation of two ordinary complex numbers. So we have, that's the conjugate of the first times the conjugate of the second. Now we want to relate this second to the ijth entry of A conjugate. That's by definition of complex conjugate of matrix. And now we have scalar multiple times all of the entries of A conjugate. That's the same thing as the ijth entry of this scalar multiple alpha bar times the matrix A bar. Okay, so we do have equivalence and we're all good. Sorry, I didn't, you might not have seen that last part. Okay, so we've got this complete. All right. All right, this one should remind you of transpose. If you take the conjugate of conjugate matrix, you get back to the original matrix again. Okay, let me pass over this proof. You can read it. These kind of get tedious seeing all these proofs again. But you can do examples to show this is true. Let me just do one simple example. If I take the conjugate of a conjugate matrix, let's just do a simple example: 1 minus I, 2 plus I, 3 plus 4I, and minus 7I. If I take the conjugate of that, I'm going to get 1 plus I, 2 minus I, 3 minus 4I, and plus 7I. Okay, but if I want 2 conjugates, then I'll have to take another conjugate, and if you take the other conjugate of this, you'll see that you get back to the original matrix. Okay, so if you're confused about these theorems, just take some simple 2x2 example and see that it works. All right, so this one says that you can take the transpose and conjugate it, and that's the same thing as taking the conjugate first and then the transpose. This makes sense because transpose is simply rearranging the elements in the matrix. All right, so these basic properties we may need when we're doing algebra with matrices. All right, so that was lead up into this section, which talks about the adjoint of a matrix. We've seen conjugate, we've seen transpose. The adjoint is the transpose of the conjugate. It's the transpose of the conjugate. Now, if you think about it, what we just showed is that the same thing as the conjugate of the transpose. So you could write it this way. Doesn't matter which order you take the transpose and the conjugate. These are alternative notations for the adjoint. Sometimes it's written as AH. Looks like he's going to write it as A star, A star. He's going to use this notation. Okay? All right. Now, here are some similar theorems to the theorems that we've shown with conjugate and with transpose. Now, fortunately, we can use our theorems that we've proven with conjugate and transpose already. So, for instance, if I want the adjoint of A plus B, by definition, that's the transpose of the conjugate of A plus B, but the conjugate of A plus B is conjugate A plus conjugate of B that we showed. Okay, the transpose of the sum of 2 matrices is the transpose of the one plus the transpose of the other. And here we have the conjugate transpose of A plus conjugate transpose of B. Similarly, with this theorem, the adjoint of alpha A is alpha bar times the adjoint of A. All right, this proof is similar to what we've seen before. And the adjoint of an adjoint is the same matrix again. All right, so that completes some of the basic matrix operations that we'll need in subsequent sections. And that's it for this video.